welcome everybody to the COSI seminar. Our speaker today is Mark Govett from NOAA. He's the chief of the Advanced Computing section, Global Systems Division. He got his BS in computer science from CU Denver and his MS in computer science from CU Boulder. His research interests include GPU, cloud computing, distributed data access, web portals, and software engineering. Accomplishments. He's developed 2 Fortran compilers, which is about as many Fortran codes as I've written in my life. Much better at it than I am. The scaling modeling system, SMS, for distributed memory computing, and the FTC-ACC for GPU computing. He's also led the exploration of grid computing in NOAA. And on a side note, he's actually a very good tennis player. Just not as good as me. So,
that's right. Thank you. Yeah. Thanks, Matt. Yeah, Matt asked me to consider coming and giving a presentation to you I think about 6 months ago, and I thought it'd be a nice opportunity to see the sort of work that you all are doing and share with you some of the work that we're doing. We're very excited about. So GPUs have kind of been something we've been aware of for about since 2008, when we really noticed that this was an opportunity for new high-performance computing that could be applied to weather prediction. Weather prediction is traditionally one of the largest users of computing. We always are out to find the largest computing systems we can get our hands on. I would say outside of the so-called black industries, the DoD type stuff we can't really talk about. Weather computing, the computing requirements for weather prediction are certainly the largest. And so our group, the responsibilities we have are to explore new computing technologies, mostly towards high performance computing, but also in visualization, cloud computing, grid computing, those sorts of things, to help NOAA be more efficient in delivering the most accurate information they can in environmental prediction, whether it's weather or climate or others. These are areas that are important to NOAA, and they're trying to do it in a cost-effective way. So you take large computing systems that cost tens to hundreds of millions of dollars. If you can reduce the cost by 10%, you're doing a huge cost savings for the organization. So there's a number of us that are involved in this GPU work. As I said, 2 years ago or so, there was just me. I started this investigation myself, and it's as over time we've been adding more and more staff, portions of their time, to do this work as it's becoming more and more of interest to NOAA. So the structure of the organization, some questions came about. NOAA stands for National Oceanic and Atmospheric Administration. The one that you all probably know about is the National Weather Service, and underneath that is the NCEP, National Centers for Environmental Prediction. This is the ones who are responsible for producing and getting out the weather products that you use when you download or get information from your favorite provider, your newspaper, and so on. They get their information from the National Weather Service, and they put quality information in there. They change it a little bit here and there, but primarily they're relying on the products that are run from weather models that are at the National Weather Service. We provide both the models and the computing technology to the National Weather Service under this part of NOAA called Oceanic and Atmospheric Research, or OAR. I'm in this laboratory called the Earth System Research Laboratory right here in Boulder, just off of Broadway and Baseline. And within that is a division, and I'm inside of that with this small group. There's 8 of us currently looking at advanced computing technologies. So in terms of model development, there's models that are being developed at the local scale, at regional scale, and global, depending on the type of weather prediction that's needed. At the regional scale, we've got a couple models here that are being developed either totally in-house at NOAA or in collaboration with universities and entities like the National Center for Atmospheric Research, which is also up here on the hill. That's a NSF, National Science Foundation funded entity that works closely with the university community. So the models are being developed here. The intent is to improve the prediction for things like hurricanes, aviation weather, fires, chemistry, ash, nuclear fallout, those sorts of things. So we're applying these weather prediction models at these different scales. 1 to 5 kilometer is the current research resolution that we're looking at. In an operational or the National Weather Service, we'll be looking at more like 30 kilometer as opposed to the 5. So we're doing much higher scale. There's a lot more science that's being brought in. There's more observations, those sorts of things that would be incorporated in a finely tuned next generation weather model. The global models, currently we're running it between 10 and 30 kilometers resolution over the entire globe. We've got a model here that we are running right now. It's due to go into National Weather Service operations in the next 6 months. And really the point of this slide is to show that the models and the increase in accuracy for these models have led to direct improvements in things like hurricane track and these other environmental events. What you see here, and you can't maybe see it so well in the back, is the actual track of Hurricane Ike as it was making landfall 2008, and then these different models that are running. Here's the GFDL model that's running in Princeton. This is a Hurricane Wharf version that's running in Florida for the National Weather Service. This is a global model that's running at National Weather Service. And then there's 2 research models that are showing up here. Those are running at our laboratory and being developed here. So the 30 kilometer you see here in blue is tracking pretty well to the actual track of the hurricane shown here in black. The 15 kilometer is actually tracking very, very nicely for this. Of course, I wouldn't show a bad case, but this is what we've seen pretty much in looking at the resolutions of models and how accurate they are. Is they do a better job as you get to finer resolutions. You can model the dynamics of motion. They're happening here over the ocean as well as in the atmosphere. You get a better prediction of track and intensity. So the important thing here is that you don't want to have your hurricane make landfall in some other place than you expected, and you don't want that to happen too often because people won't evacuate if they think that they can't believe the weather forecast. So right now we're looking at tracks that are pretty frequently in the neighborhood of 50 kilometers. So 50 kilometers, you'd have a swath of people that you'd be asking them to evacuate from an area where the hurricane is going to make landfall. In terms of the computing requirements, to run one of these 15-kilometer global models at the laboratory takes about 3,000 cores. And then they have this ensemble, which is multiple members that are perturbed in a certain way, whether it's different initial conditions that are being fed into the model or slight variations in the model itself. So different physics, different dynamics, all lead to slightly different predictions, and then those are combined together in an ensemble, and probabilities are then stated from the prediction of each of these tracks, if you will, to come up with a probability distribution of the likely place that a hurricane would make landfall. So just running one of these 15-kilometer with 21 members takes 126,000 CPU cores. It's a big amount of computing, and we see that the trend here is going up very, very quickly, well beyond what NOAA's computing capacity is today. So where we're headed in our research models is 2-kilometer global scale horizontal resolution. And this will lead us to better predictions in hurricane track and intensity and some science in the regional climate area, looking at weather in the 1 to 2 month scale. Making predictions out that far is beneficial for planning. For instance, if you have droughts or if you have flood or you're expecting certain trends, then people can plan for that kind of thing, and it's very valuable. There's a huge amount that can be saved there in terms of property and people. So there's a number of active developments in this 2-kilometer resolution, so-called global cloud resolving scale. Some in Japan, there's one up here in Colorado State. GFDL has another one, and we have one we're developing right now, and I'm going to talk quite a bit more about that. The computing requirements for running at 4-kilometer scale for the CSU model took about 80,000 cores of DOE Jaguar, which is the largest, or was until recently, the largest computer in the world. The simulations ran at about 50% of real time. So not really useful for weather forecasting if it takes you that long to produce a weather forecast. But you kind of get a sense for the problem here, which is if you want to run at this scale for improving things like weather, severe weather events, you're going to have to do something about solving the number of computing resources that are needed to do it. So this is the NIM, the non-hydrostatic icosahedral model. You see a picture of the grid here. You can't see too well in the back probably, but these are all hexagons. They map very well over the globe. This is in contrast to a lot of models which have problems, so-called pole problem, which is that as your longitudinal lines get closer and closer together near the pole, modelers have to do special things in order to be able to resolve what's happening up here where the grid points are getting so close together. So they play some games and other things, and it leads to eventual instabilities in the model and inaccurate results. So this is a non-hydrostatic model. That means we can go to very fine scales, targeting 2-kilometer resolution. It's uniform. All of these grid points are almost exactly the same size, as close as we can get them. Dynamics, the dynamics portion of this model is complete, and we're integrating physics at this point. We, as in the scientists who I work with. It uses in the grid here, you can imagine trying to find elements and index your way through this. Might be a little challenging because these are 6-sided shapes. We use an indirect addressing scheme that permits the code to be very concise and efficient. And this was designed for GPU architectures because of the problems I talked about in terms of computing. Is the choice is either you can't run this because you don't have the computing, or you look at new technologies that would allow you to do it. So we're estimating right now about 5,000 GPUs will be needed to run this in this operational benchmark of 2% of real time. In contrast, we think that about 200,000 CPU cores would be needed to do this, and we don't think we could hit this 2% of real-time mark. So it's a big deal in terms of the computing required. So now I'm going to talk a little bit about GPUs in a general sense and introduce these to you in terms of the hardware, and then talk about some of the software innovation that we've done here. There are 3 manufacturers of GPU and multi-core: NVIDIA, AMD, and Intel is going to have an offering here sometime this year. We'll be looking at that in beta version later this year. NVIDIA was the first one to support HPC, and the reason why is because they did things like support for double precision and some specialized memory that was needed called ECC memory, error correcting memory, that would allow us to repeat results. So you don't want to have, in the video world, it doesn't matter if you've got a bit that flips. Generally in video gaming, you're not going to notice one little pixel on the screen somewhere that flipped. But in the weather world, when you're doing long-running simulations of 7-day forecasts or longer, if you start flipping, inadvertently flipping bits, you're going to lead to potential instabilities in what the model is going to produce. So that's just unacceptable for us from the weather world. So NVIDIA is the leading one right now. They're providing the kind of capabilities we need for scientific computing. AMD has still got its foot squarely in the graphics side, but they recognize tremendous potential for using this at high-performance computing as well. And Intel's taking a slightly different approach in this. They're not doing what we would think of as a GPU, and I'll explain that a little bit later. They're looking at using the technology they already have in the CPU world and extending it in more simpler ways without having to do major changes. They got a lot invested in their CPU architecture. So you can see the performance curve, and this is what really attracted us, what was going on. This is the Tesla, that's the predecessor to the Fermi here. You can see the GPU performance curve is going up quite nicely, at least through 2008. And the CPU is, we know it's been relatively flat. They're not getting the kinds of performance gains that they had in the past. So what they're doing is they're adding more and more CPU cores on a chip. So you can have now 6 or 8 cores on a single chip. GPUs have on the order of 500 cores on a chip. Oops. So here's a look at the hardware specs for the various GPU offerings. You see here the number of cores. AMD has the most here, and these other ones have different offerings. You can see the Intel approach allows you 32 cores, and this is a conventional CPU. That's the latest Intel offering, Intel Westmere, with 6 cores. The flop counts in single precision and double precision. You can see the tremendous amount of opportunity here for GPUs as opposed to the computational performance of a CPU. Memory bandwidth turns out to be a big issue for us in the weather world. We need to be accessing lots of data, and we need the memory bandwidth to be sufficient to get the data to the CPU or the GPU core where it can do its work. And the power is also an issue when you're starting to stick thousands to hundreds of thousands of these things together, is how much power you're going to need to be able to bring a system, huge system up and pay for the power bill. So here you see a little comparison I put up here showing a GPU chip which is fairly large. This is about 3 billion transistors. This is the 2009 Intel Nehalem processor. Had about 700 million transistors. So this one, in terms of complexity, is about 4 or 5 times more complicated. And they've had some issues early on with manufacturing these things because it was a total new level of complexity in terms of being able to produce these things efficiently. So they were slow to get them out. Westmere, as I said, six cores, 140 gigaflops, and there's the performance to power ratio, 1 gigaflop per watt. On the GPU side, the current release, actually they backed off on, because of manufacturing, they backed off on this 512 cores to 480, and it has on the order of 5 gigaflops of performance per watt. So these things are great in terms of the potential for doing lots of work. They have a lot of computing capability, but in terms of programmability, this is where really the challenge is, and really where our team has done our work, is being able to get these things to work really relies on understanding the memory layout, the way in which work can be divided up and efficiently given to the GPU to do its work. So in GPU land, you have your main memory, which is global memory. These are sort of elements of global memory with slight variations. But global memory is on the order of, nowadays, on the order of 4 to 6 gigabytes of memory for the GPU chip. And then you've got local memory, which is relatively slow because it's drawing off of this global memory. The real fast memory is showing up here in the shared memory, which is small, and registers. So the trick in programming is to try and get the things that you're going to need from global memory into shared memory or registers as much as possible, so that the computations on in these threads can be done very rapidly. So it's about moving data from here up to here, doing your work, and getting it back to global memory again. And reuse. Memory reuse is also critical. So it takes in shared memory and register space, it takes about 1 or 2 cycles to access memory here, and hundreds of cycles to access memory here. So in terms of GPU parallelization, the way that you would approach getting your code to run on a GPU, there's 2 approaches. One is the accelerator approach, and the other is the whole model approach. So in the accelerator approach, you'd look at a set of routines that you have. You'd figure out which one is consuming the most resources and say, okay, that's the one that I want to run on my GPU. So you develop your GPU version here, shown in red, S2. You run S1 on the CPU, transfer your information to the GPU, execute it really fast, and then transfer the data back and continue on your way. So you're doing select routines for acceleration. The problem with this approach is that you've got a time required to copy from the CPU to the GPU, and this often overshadows any performance gains you get by running it really fast here. So this has limited benefit, but if you've got places where a routine is consuming huge amounts of time, it can prove beneficial to even do this. But we recognized early on in our weather codes that we couldn't do that. We should try this whole model approach, which is to run everything on the GPU. So in the model, you'd have your initialization here, and then instead of running dynamics on the CPU, we run everything on the GPU, we do the physics on the GPU, and we output the final results. Or a variant of this is if you've got output that's happening for model forecasts where you need to output every hour, you have to add in those cycles. But primarily the work is happening here, and there's a lot less copying of data between your GPU memory and your CPU memory and back again. So this is a much better way to go, and it does require conversion of a lot of code, and I'll talk about a little bit of that in our world where the code is not written in the language that the GPU wants to see. We have to do some work to make it work efficiently there. So there's two approaches in language, languages you can choose. One is to choose the native language that's available to you on the GPU, and that's CUDA for the NVIDIA and OpenCL for both NVIDIA and AMD today. It's unclear what Intel is going to do with their approach for the programming of the Intel offering, but my guess is they're going to try and stay with this OpenCL language, which allows you to be portable across a number of different GPU and multi-core architectures. So in this approach, the language approach, the user has control over the coding and the optimizations. However, some of the optimizations may be specific for a certain architecture, and you would find it hard to move a model from one machine to another. In the directive-based approach, you insert a directive that appears as a comment in your code, or a pragma if it's in C land, and it is benign for running on a CPU or other elements, but it would be included in the compilation, so the compiler would come in and make analysis of your source code plus these directives to come up with an efficient machine language code. So in this, the benefit is that the scientists can maintain a single source, and you can run this same code in serial parallel on the CPU or on the GPU. So your compilers, the maturity of the compilers is really what will allow you to do efficient analysis and generate the code that will run efficiently on your target machine. So it puts a little bit more of the burden on the compiler. In our world, we work in Fortran, which for some of you may not even be aware of it. Maybe you are, but certainly Fortran is not what people are working with today in general, but I would say in the scientific world, Fortran is the language that people use. And I think there's been, it'll probably continue to stay because there's a tremendous investment over time from graduate students that have developed their, Fortran code that's some science element that's going to be included in a model, and it tracks over time to include more and more of these research-oriented methods or parameterizations or other things that a model would use until it finds its way into an operational model, which could be 10, 20 years' time. So Fortran is going to live on. I think if you're going to work in this world, you kind of have to accept that, okay, I have to learn how to run in Fortran, and it's not such a bad language, really. It actually is pretty good. So the idea for us is the Fortran code is often in these modeling systems quite complex. So you might have your model dynamics and physics and chemistry and other components that are sitting here, and they're combined in some way to form a model like the NIM that I just talked about, or like the WRF that has been developed at NCAR, or other research or operational models. So these are all written in Fortran. They're complicated. We don't want to change them. Sometimes we can't change them because the modelers have died. Sometimes we can change them, but we have to get buy-in by the modelers and so on to accept the results are going to be a little different. So then you've got this box here, which is the compilers, whether it's for CPUs or GPUs, and various tools that would allow you to take your Fortran source and run it on a variety of CPU and GPU architectures. And for us, we run it at a variety of computing facilities wherever we can get our hands on resources. So at NOAA, at Navy, National Science Foundation has some nice supercomputers, and DOE. And we want to have it ideally be the same Fortran source, so we're not having to maintain a bunch of different codes. So with the NIM, what we did in 2008, 2009, we started doing this GPU development, and at the time there wasn't a Fortran compiler available for us for GPU land to convert our codes from Fortran into CUDA. So we developed one. Some of you know I have a background in compiler development, so I was able to put this together fairly quickly, and then we've tailored it as we've gone on to make improvements where it was important for us in the development of this code. We took this compiler, parallelized the model dynamics, and we did some tests comparing the 2008 generation GPU versus the same generation CPU. And the results here I show are for two different versions of the NIM model, showing that for the GPU, we're running about 26 times faster than we were on the CPU, and 33 times faster for a higher resolution version of the model with more data per processor or more work on the GPU for it to do. And GPUs seem to like work. They do this because they can hide a lot of the memory accesses that I was talking about by doing other useful work while the GPU certain data is being waited to load from global memory. Then we ran these same tests using the current generation Intel Nehalem versus the current generation GPU and got more or less the same results, 25, 26x performance improvement. And coming from a background in high performance computing, typically when you get a performance benefit, you're going to see something on the order of 5 times performance benefit in some new technique that you do. We really hadn't seen anything of this type before. This was really astounding to us that we could get this kind of performance speed up by using this new technology. So we're very, very excited about this. In 2010, we took this from running on a single GPU to running on multiple GPUs, and this requires an extra step. That is to copy from GPU to CPU that we always did, and then copy between the CPUs to get over to the second GPU in this diagram. We use this library that we developed in-house called SMS, a scalable modeling system that allowed us to do communication between CPUs using a technique called message passing. I'm not sure if any of you are familiar with that, but I'm not going to spend any time there. If you have questions, I'm happy to answer them. So this work did some elements here of first updating the model itself. It's an active development. And we evaluated some GPU compilers that were available to us now that weren't at the time we started. We evaluated this new Fermi GPU architecture, and we've been running on multiple GPUs with some modifications to our GPU compiler, updates to our scalable modeling system, and use of a system that we have in-house, 10 Tesla and 10 Fermi GPUs. So to look at and do the comparison between the compilers and what the landscape looks like today in terms of GPU compilers for Fortran, there's 4 now. There's one from PGI, Portland Group. There's our in-house compiler. There's a company called CAPS. It's a French company that's got their own GPU compiler. And Cray has now jumped in to provide a GPU compiler. Theirs is a little different, is that instead of using these intermediate languages that the vendor supports, they're going directly to the machine-like level language that NVIDIA supports. So that's a different approach, and we're currently evaluating how well Cray is doing in the development of their compiler. So you can see the way that some of these languages, OpenCL I mentioned, can support all of these, potentially support the Intel, but certainly supports the 2 GPU offerings that are available today. And then CUDA, which is really for the NVIDIA side of things, and unclear that they're going to allow it to be used elsewhere. So in terms of the general compilers, None of the compilers support all of the Fortran language constructs. It's a big language, and it's going to take a while, if they ever get around to it, to do support for all the language. They just restrict what things they currently can provide right now. So this company, CAPS, provides an extensive set of parallelization directives for analysis and optimization, and it can generate both CUDA and OpenCL. PGI has two compilers, Accelerator, which is directive-based, and a native language called CUDA Fortran, which is Fortran plus extensions that support calls to the GPU and some issues around GPU memory definitions and access. And then F2C that we developed in-house, developed here for our models and requires some hand tuning in order to get optimal performance. This one generates just CUDA. So the directives look like this. There's directives to support kernel generation. There's regions that you can define for acceleration. There's parallelism that you define for do loops or for loops in the C world. And there's a directive for data movement. There's some other ones which are I have omitted here, but there's enough of them that we can get our codes running on GPUs using this compiler. So it uses the F2C uses a compiler building tool called Eli. That was developed here in conjunction, here at CU Boulder in conjunction with university in Australia as well as one in Germany. Together they did that work over the last 20 years, I would say. Bill Waite was one of the head people in doing the development of this compiler tool, and that's been the basis for which this F2C compiler was developed. It handles all the parsing of standard Fortran 77, 90, and 95 features, and it does translation as we've needed to support the codes that we have, and we're adding new features and capabilities as we need them. Right now it covers about 98% of the translations we need, and some additional work is needed to get the code to run efficiently, but we're effectively there in the work we do. If we can't support a language construct, there's a nice little error message that comes out that points you to the line where the language construct is, and you can make changes or modify it as you need to eliminate it. So it uses macros to resolve array references. So in Fortran it's very nice. You have 2 3D arrays. Certainly a lot easier to work with multi-dimensional arrays in the Fortran world. In the C world, it means setting up pointers and other things to access those elements. So what we do is we just collapse all of the array into a single dimensional array and then find the point where the data is given the number of dimensions and the size of those dimensions and so on. It generates also the copies to go from Fortran to C or CUDA, and it generates the routines, kernel routines that run on the GPU. CAPS has their own compiler with parallelization directives. It takes a minimal set of directives to get the code working, and the compiler is very conservative in what it'll do, and it provides you some nice diagnostic information. We began our evaluation about 4 months ago, and there's very good documentation in this tool. PGI provides acceleration directives similar to what we do with the F2C for accelerator regions, accelerator do, and data resident for having data, managing data on the GPU and the CPU. So in taking the NIM code, it's important to stress that in order to achieve the high performance that we got with the NIM model or other Fortran or C codes or other things, is that you have to understand your code and know that the best optimizations you can make are the ones that are in native language. Once you've got that code tuned and running well there, and you've looked at the algorithm, you understand the target for the architecture, you're better off in terms of doing that work up front and then trying to move it over to your GPU. So understand the algorithm first. So in this case, we did this with profiling, and we identified that there was a matrix solver inside this model. Basically, this model is a series of dot products, and it was designed that way because we knew the kinds of performance goals that we had. This matrix solver, which was just a BLOS routine, I believe, was 40% of the runtime of this model. It was being called 150,000 times per time step in a very modest size resolution model, and 3.6 million for the next size up. We're in this model resolution where these are about 270 kilometer resolution and 135 kilometer resolution. So we had a long ways to go to get to the 2 kilometer scale, and you can see these numbers coming up. So what we did was we replaced the BLOS routine with a hand-coded solution that immediately resulted in a 3x performance increase for the entire model. And then we did some loop unrolling to improve the overall performance by another 40%. And it was this that we handed to the GPU to ask it to do its efficiencies as well. So this work up front was really important. We also organized the data so that the inner dimension would be used for the GPU thread calculations, and this improved the way that the GPU was accessing slow memory. There's some things on the GPU that are provided to you to optimize the performance of how you access and work your way through memory. And then finally, we did some reordering of calculations to improve data reuse in the model. For the parallelization factors for the model, code design was the dominant factor in terms of achieving high performance. Weather codes in general typically have a high number of memory accesses to the number of computes. So the typical pattern is you have some arrays, you move them in, you do 1 or 2 calculations by your compute unit, and then you move it off again. There isn't a lot of this where you're keeping it in memory and just continuing to do a whole bunch of execution, keeping that data resident. It's being moved from memory to the GPU and then out. And so this sort of thing means that you've got to pay a lot of attention to how you're striding through memory. And data alignment here in making code changes to our code led to a 10 times improvement in the model performance, just doing that. So there's some big wins here in terms of how we designed the code based on the architecture we had to work with. The data dependencies in the model guide the parallelization, and alignment is the crucial issue here. So dynamics, the dependencies are in the horizontal. You see here a ij is horizontal as you're striding across the surface, and k is the column of the atmospheric model. So dynamics, we put the vertical component on the inside so we could thread across that in parallel, and the horizontal elements were that followed. In physics, it's the reverse. So now we have dependencies in the vertical as you're going up and down in the physics in the column, and the horizontal has no dependencies between them, so we can parallelize there. And this implies that a transpose is needed to move from the dynamic space to the physics space. So in terms of optimizing for the GPU kernels now, taking the code and moving it to the kernels, we use a performance profiler to identify the bottlenecks. And there's a couple fairly simple tools, and they've gotten a little bit better recently. There's some graphical tools to work with that help you identify how well the resources on the GPU are being used. One of the elements is called occupancy, which is largely determined by how much registers and shared memory you're using. Another is coalesce loads and stores. This is a technique in which you can access memory more efficiently based on how you're organizing your arrays. And then the use of shared memory or registers where there's data reuse. So if you do have any kind of data reuse where an element, an array, a scalar is being used again and again, it makes sense to try and get that into a register or into shared memory so that you can get a performance win there. So in the performance comparisons we did for the GPU compilers, we're really interested in using the commercial products. We don't want to continue to maintain a compiler of our own. It's not in our business to do compiler development, really. So it's been an effective tool to go back to the vendors and say, hey, we're performing, better than you are, so what about it? We got to pay for your compiler and we're getting ours for free. So this has been a great way to get them to respond to us, and they've done a pretty good job in terms of, especially the CAPS HMPP compiler has done a pretty good job with giving us performance that's on the order of what we're seeing in our local in-house compiler. We expect in time that compilers will exceed what we're doing in the in-house compiler, because they'll do the additional work to do analysis to provide much more efficient code than what we can do ourselves. We're a team of, well, it's one half a person, that's me doing this work here, compared to some of the teams of compiler developers that are happening out here. So we're expecting to see some improvements here. PGI is a little bit further behind. Some of the code doesn't work at all. Others, we're working with them to get them to have the performance improve a lot for us. But we're very encouraged by these results. So this is the generation from 2009 comparing, you can see these 26 performance, X performance improvement overall, and some variation that you see here between the compilers. These are all good because we can look into why is this compiler doing better, why is it not. A higher resolution version of this, it looks like I have a little typo here. This should be the higher resolution, 10,000 points, horizontal points. And this is the current generation GPU versus the latest generation CPU. And we're still seeing about 25x performance improvement over the Intel Westmere single core. We did just recently run on using the full Westmere node, which is 6 cores as opposed to 1. And so these numbers will go down, and it turns out they go down by an order of 4 times. So you're getting about 4x performance improvement with a 6-core Westmere. So you'd see these numbers come down instead of being 25 if you're doing socket-to-socket comparisons now between a GPU and a CPU. You'd see this number be somewhat lower. In terms of the compilers, these other compilers, we're still waiting on some upgrades that they need to do in order to run in this Fermi environment. In terms of parallel computation, we have a single problem size that we have to work with, which is this 10,200 points. And we don't have, the modelers haven't given us a bigger problem. So each time we add another GPU, we have to cut the number of horizontal points in half. So our problem in blue here, you see the compute time, and this is going down because the number of points or the amount of work that has to be done on the GPU is also going down. Communications, once you get to 2, you got to do comms between the GPUs, is staying pretty much the same through the different numbers of GPUs, and that's what we expected to see. So where we will go with this when the modelers give us a bigger model to work with is we'll stay at about 10,000 points of work per GPU. So this blue bar will stay the same across here, and you'll have this extra amount of time spent doing communication between the GPUs. So this is very encouraging. We're feeling like right now the comms are not a big part of the overall compute time that we expect to see on a GPU. So back to the projections for a GPU. Our goal, as I said earlier, was about 2% of real time. And using the numbers that we've shown here, factoring in what we expect to see as improvements in GPU technology going forward, we believe about 5,000 GPUs will be needed to run a 2-kilometer version of the model in 2% of real time. That's our goal. That's what we expect to see in 2013 in this development effort. We're assuming that we're going to get about 20 times performance improvement. I think we saw on the previous slide, the previous 2 slides, that we're about there right now with 20x. We're assuming, as I said, 5x performance improvement in the hardware, and we're assuming that we can run all of dynamics and physics on the GPU, and communications times are scalable. We've seen nothing to indicate that that won't be true. So as we look at a system of this size, it was useful to look at the hardware and the cost of what the hardware would be. The DOE Jaguar machine is the largest, or was number 2 now in the world. It was just passed by a GPU system some months ago. It's 2.3 petaflops, it's got 250,000 CPUs, 284 cabinets, and it consumes 7 to 10 megawatts of power. That's sort of a good chunk of the Valmont power plant down here. So, there's some concern that, the power bill, incidentally, for this was estimated to be about $5 million a year just for powering up the Jaguar system. So pretty intense. The cost of this system was $100 million just for the hardware, and then they had to build their own building to put this in and put in cooling and power and all sorts of innovation that went into this. This was an incredible engineering feat, I think, putting together a system of this size, and but it costs a tremendous amount, $75 million. So you look at an equivalent GPU system, 2.3 petaflop. You're looking at 2,000 Fermi GPUs, 20 cabinets, consume about a megawatt of power at a cost of $10 million. So 175, 10, I think it's pretty clear the case for GPUs in terms of just hardware alone is extremely compelling. In terms of reliability, this is something that we also look at in operational systems, is how well is the system going to stay up over time. If we're actually running a weather model that we care about and we want to make sure it produces a forecast, we don't want the system to go down regularly in between these model runs. So reliability on the operational machines needs to be 99%, 99.9, it might even be 4 nines, but it's very, very reliable is the requirement. And clearly here the reliability in the Jaguar system is very much in question. GPU reliability week certainly looks a lot better. You could run multiple ones of these side by side as is currently done at the National Weather Service to get your 99% reliability. So there's big problems with what we see here, and GPUs certainly give us an opportunity to continue moving forward in our scientific models and producing more accurate forecasts. So I don't know how long I had or how much time. Am I okay? Yes. Okay. So in conclusion, the GPUs and multi-core are the future of HPC. I think that we've done tremendous things in the CPU world, but as you see in technology, as we get further and further towards the extreme, it costs more and more for you to continue to see innovation in a technology. So you always are looking for new technology to answer the call of requirements that people have in the scientific community and others. So right now the GPUs are number 1, 2, 5, and 8 in the top 500. Expect this to be dominated by GPUs within the next couple years. They're really, all the vendors now are offering GPUs as part of their offering for people buying big HPC machines. The roadmaps for GPUs look very strong, and the emphasis is on high performance and the power ratio. So how much power is being consumed is really become an issue as we look at siting, we look at power costs and other things. Building giant systems requires us to pay attention to that. There's also a nice thing that's happening by the vendors, which is an integration of the CPU and GPU on a single chip. So you won't have the issues of communication that's quite slow today. This will improve somewhat in this integration of these two elements on the GPU. The CPU will actually be a fairly lightweight entity, what I've seen in a lot of what the vendors are proposing, so that the workhorse will be the GPU. Memory will be able to access between CPU and GPU uniformly, so you can reach into CPU and GPU memory with some cost. You certainly have to still pay attention to how you're accessing memory. But we think this is going to solve a lot in terms of some of the performance issues we see with big systems. In terms of the model development, the dynamics is complete. We're just staying up to date with what the model developers do. We've seen this 20 to 25x performance improvement, and we're working and waiting really on the science to come up on the physics so that we can integrate that in as well. We're expecting testing to begin on a very high resolution model in June, and it's depending on what kind of computing resources we can get our hands on. So final thoughts here. The code design has been the dominant factor in performance. Certainly alignment of data, it leads to improvements, so you want to look at your codes, make sure that you understand how the codes are doing things and how to be efficient, understand how GPU works and so on. Dependencies guide the parallelization you see here. Performance tools are improving, and they really help you to determine what the speed up potential for your code is, how resources are being used, and what kinds of improvements in locations where you could do better and focus your attention. Debugging's challenging. Potentially you've got millions of threads that you've got to manage on a GPU in a multi-GPU environment, so you need to have robust debugging tools that allow you to get to your problem and solve it fairly quickly. That's coming along. There's a couple products right now that look like they're going to be keepers in terms of debugging in this highly scalable GPU environment. And the compilers are maturing as well. F2C is largely just translating the Fortran into CUDA, so we expect that really as these commercial compilers mature, they're going to do a lot more analysis and optimization of the code. So there's a lot of good science that's happening at NOAA, and I want to just put a plug in for this. There's also, jobs in various places in NOAA, and I would encourage you to look into what opportunities and what your interests are. The science that's happening in weather and climate where we are, there's also a lot of good work happening in chemistry, land surface, remote sensing, use of satellite data, radar data, that sort of thing, development of new instruments, high performance computing, and a whole host of other things. I will say, there's a lot of variety, and it's a really interesting place to work. If you, have an interest in a career in science, working in computing, visualization, check out some of the websites. For instance, there's the Holling Scholarship that offers scholarships for interns either in the summer or during the course of the year. They're for graduates and undergraduate students. These are an opportunity for you to get some good work experience, see what the working environment is, whether you want to continue a career in science. It's an opportunity for us also to see you and see how well you're fitting into our organization. So, getting work experience along the way is going to be way better in terms of your career than waiting until your degree is done and then going out and trying to look for a job. And I can tell you as someone who hires people that I'm actually looking for work experience that is close to the field, or at least a demonstration of your ability to work in a professional environment. So I'd encourage you to check that out. There's other places in NOAA that offers scholarships. I've just listed this one, but you could do a Google on that and you'll probably find some other links to where NOAA is. You can also contact me. My email's down here. If you have an interest, I would be able to potentially direct you to a place where you might fit in or might find an opportunity. Okay? Thank you.
We have time for some questions.
Double?
That's a good question. So initially, when we started doing this GPU work, there was no support for double precision at all. It was all single precision, so we had no choice.
Okay.
But we knew this was going to be an issue going forward, and we had to kind of gauge whether the technology was going to support us. When I went to the first GPU tech conference, they hold them every year in San Jose since 2008. The tech conference at that time was an amalgamation of the gamers, coupled with these aging the scientific programmers, and there was no recognition that there was an opportunity at that point for high performance computing until they realized that there was, some of these old guys that were showing up trying to, see if they could get this high performance computing for them. So they only supported single precision at that time because that was sufficient for the gaming community. What NVIDIA has done since then, and I think it's been a fine marketing thing, but also a strategic thing, where they recognize that gamers and games in general are more realistic when you can incorporate real science into the simulations. So now you have, for instance, the movie industry with all the special effects and things. All those special effects are based on a lot of the equations that are governing equations for atmosphere, for fluid flow, and other things. And all that stuff can benefit with double precision. So they went from single precision into double precision to both support where they expected the gaming industry to go with higher and higher resolution, more and more realistic gaming environments, and scientific computing, which required it in order to continue to use this as an HPC computing platform. So it was a really good thing, and I think AMD is playing catch up on this, is to provide the double precision support that we need, as well as some memory issues that we have to have in our computing environment. And they're getting there, but having double precision is key. So just a little bit more on this is in terms of the development of the model. There's some places where double precision is really needed in the weather and computing environment. Primarily it's in the physics. The physics is where there's a lot more round-off errors and other things. It's finer scale where calculations, it makes a bigger difference in terms of getting your physics right. In terms of dynamics, you primarily can write your code such that if it's well written, it can be written in single precision. You can get away with that. This all depends on one model versus another, how well the equations have been written, numerics have been written to ensure stability of your code, to reduce round-off error and other things. Numerical analysis is great stuff for this, and having people that are modelers that would incorporate this into their thinking leads to being able to run much faster in single precision than having to resort to double precision to get the same result. So that's kind of a long answer.
Yeah, and double precision is handled in the processor as opposed to handled at a higher stage in the compiler before?
Right, before, yeah. You could do it very slowly. They did have a double precision unit, but it was, the numbers that I showed up here were, instead of being a teraflop of computing in single precision, double precision was on the order of 80 gigaflops. So you lost a huge amount. Now in the current offerings, you're really at roughly half the speed for double precision versus single precision, which is about what you expect, using twice the resource. So it runs half the speed.
Thanks.
Yeah. Yeah.
What do you think about the growth of high performance computing? To explain myself better, till now high performance computing is all about teraflops and petaflops. But then I recently read a report where it's impractical to go beyond that, especially regarding power consumption. It's just getting too huge.
You mean in terms of the capacity for how much bigger can computing get? On the drawing boards, they're putting up this theoretical exaflop investigation is 1,000 times more powerful than the petaflop. And it's really amazing to me how quickly the marketeers have moved from what is just barely realizable right now, which is petaflop computing, into 1,000 times more than that. And I guess maybe it's to attract funding because now there's an opportunity to get investment by government and by research groups to try and get there. But the exaflop, the power is going to be the big issue. And that's why the vendors are paying a lot of attention to how much they can keep their power consumption down. NVIDIA in their announcements recently has said that their power requirements in the follow-on generations of GPUs will not consume more power. And in fact, they've got this green initiative, which green computing, I believe it is, that reduces that significantly. And there's some work that's been done in this area that is very useful. The IBM machine, I'm forgetting the name of it. There's an IBM machine that is very novel in its use of power and computing. And so it's done some real, Blue Gene. So Blue Gene is this one which is being used as a basis for designing some of the exaflop type systems. Is how do you approach minimizing the power requirement to get potentially to big computing that science feels like they need in 5-10 years time. It's about a decade between, normally it's about 10 years in the generation of going from going to 1,000 times bigger. So when we went from teraflop to petaflop, that took about 10 years, and now we're looking at the same thing for exaflop. But there's a lot of investment in research that's going into that right now. Yeah.
Last question.
Oh, it is.
So you said you're using MPI techniques to stitch together multiple GPUs. What sort of fabric does it take to not have that be a horrible bandwidth limit?
Yeah, so the best that's out there right now is things like InfiniBand, which does get you part of the way. But this is probably one of the crucial issues with putting big systems together, is that if you have a lot of work to be done on an individual node, a lot of compute work, then the amount of time that you spend in communicating will potentially be less. It's not guaranteed, but it'll potentially be less. To reduce the communications is always going to be the weak point in building these big systems, and it is even in the CPU world today. So there's things in writing your code which can help reduce that, to try and reduce the frequency in which communication is done. In the GPU land, what we do is we say computes are basically free. That it doesn't cost anything to do an extra computation. So if we have to do duplicate calculations happening on this GPU and on this one, we don't worry about it, we just do it. In order to minimize how many times per model time step that we have to do communication. In the CPU world, there's also a technique called aggregation, which is that you combine all of your communication together. So if you've got multiple arrays that you want to communicate, you combine all of that communication together so you only do one message send as opposed to multiple ones. That's also a way in which you can reduce communication time. But when it's all said and done, it's the thing that we're going to pay attention to most is the communication and what sort of support the vendors can provide in giving us the best hardware possible to move data around. Yeah, it's a good question.
Thank you all for coming, and especially thanks to Mark.
Okay. Thank you all for coming. Okay. Hopefully I didn't take too long. Okay.
Oh, no,
That's good.
Perfect on time.